Our next speaker is Zhou from Hong Kong Polytechnic University. He is also a recipient of Frontier of Science Award. He will talk about numerical methods for non-local models. Let's welcome.
Okay, so thank you for the introduction. First of all, I would like to thank ICPS for the kind invitation and this important award. It's my great pleasure to be here and deliver this lecture. This is a joint work with Marta from Stanford, Professor Changdu from Columbia, Christian in Sandia National Lab, Xiaochuan Tian from UCSD, and Max Gansberger from Florida State. And this talk will give a brief introduction on the nonlocal models and its numerical methods. So in the beginning, let me explain what is nonlocal model and what's the difference between local and nonlocal. And we say that local models are the models only involving local operators. Okay, then you can think about what is a local operator. We say a linear operator L is a local if you apply this operator on any function. Then the resulting support should be smaller than the original one. Then this operator is called a linear, okay? Then according to Schwarz-Kernel theorem, any linear operator can be written as an integral, okay, with a kernel function. If we want the operator be local, then the only choice for the kernel is the linear combination of a direct delta function and its generalized derivative. And the corresponding operator is just a polynomial of derivatives, okay? So the PDEs are local models and the only ones. All the other continuum models are non-local. So compared with classical local PDE models, the non-local models encompass a broader range, okay? This talk consists of 3 parts. So in the first part, I will give some motivating examples about the non-local models, and hopefully I can convince you that non-local models are both common and useful. And in the second part, I will introduce some mathematics theory, right, behind the non-local models. And in the third part, I will introduce some popular numerical methods for solving non-local models. So the first example about the non-locality comes from the model reduction. Okay, so you can think about this trivial example. It is a large linear system coming from numerical discretization of local PDEs. Because the continuum model is local, so the resulting linear system should be local. That means all non-zero components are concentrated around it, around the diagonal part. Okay, now we want to get rid of y. So how to do that? From the second equation, cx plus dy equals to g, we can solve for y in terms of x. Then plugging this relation into the first equation, ax plus by equals to f. We got a linear system only for x, right? And the resulting system is much smaller than the previous one, but it is non-local. Why that? Because it involves inverse of d, okay? Even though the original matrix is sparse, but if you take an inverse, it could be a dense matrix, so it's non-local, okay? And a similar argument also works for reduction of ODE. Now we have an initial value problem of this ODE, and we want to solve x of t, y of t. Then from the second equation for y, we can solve for y in terms of x, right? Then by Duhamel's principle, it consists of 2 parts. The exponential td times y0, okay? And the other part is a convolution between exponential td and the cx, right? Then you plug in this relation to the first equation, you got an equation for x of t only, but it involves a non-local in-time operator, right? Which represents some memory effect. So you can see from these 2 examples, the non-locality often appears when we do the reduction of variables. Okay? So that's the first example. And the second example is for numerical analysis. the nonlocal models can help in the development and analysis of numerical schemes for solving local PDEs. One example is the smooth particle hydrodynamics, okay, SPH. And the key idea is to use nonlocal relaxation to the local mechanics. So roughly speaking, it consists of two steps. In the step one, we do a nonlocal approximation to the local differential operator, okay? So this is an integral with a kernel function W delta, which is a smooth function. And the delta denotes the distance, the radius of the support of the function. Okay, so it has a finite support called delta. And in the step two, we can do some particle quadrature rule to discretize this integral. Now we got a discrete system which can be solved by computer. And in the second step, we introduce the spatial resolution scale h, which represents the distribution of particles, right? However, there are some numerical issues, and first of all, the resulting numerical schemes might be unstable. And besides, the choice of delta and h is very important. The different choice will give you very different solution, okay? So then the nonlocal models helps a lot, okay, in the numerical analysis. For example, in the step two, we got a nonlocal solution, we got a nonlocal model after we do this nonlocal relaxation. So we can check the well-postedness of the resulting nonlocal models. If it is well-posted, we can proceed to the second step. If it is not well-posted, then it is not reasonable to search for a good numerical scheme, right? And in the second step, we prefer to construct the numerical scheme robust with respect to delta and h, okay? So the message is, even though our target is to solve local PDEs, but the nonlocal model can help us develop and analyze numerical schemes. Okay? And the third example is for modeling of anomalous diffusion, right? We are familiar with diffusion equation. The first order derivative in time is proportional to the Laplacian in space, right? At microscopic level, the diffusion phenomena is due to the Brownian motion of particles. One important statistical law of Brownian motion is that the mean square displacement of a particle is proportional to time, okay, linear in time. But in many experiments, people find that this scaling law is not always true, okay? And the anomalous diffusion is a process when the mean square displacement of the particle is not linear with time. One typical example is this power law, okay? It's proportional to t to power alpha, with some power alpha is not 1. There are a lot of examples where people observe anomalous diffusion, like the RNA movement in bacterial cytoplasm, or contaminant transportation in underground water, or the movement of ultra-cold atoms and sticky colloid particles, okay, and so on. One popular model to describe anomalous diffusion is called a subdiffusion model, which is nonlocal in time, and this model can be derived using continuous time random walk, which is a generalization of Brownian motion. In continuous time random walk, the particle could stop at a certain position for quite a long time. And if the probability density function of the waiting time satisfies some heavy tail distribution, for example, it satisfies the power law, okay, in this way with alpha between 0 and 1, then the corresponding PDE model is like that, right? The first order derivative in time in the classical diffusion model is replaced with a nonlocal in time fractional model, which is defined in this way, okay? The integral is from 0 to infinity, okay? And this nonlocality represents some memory effect. And in our previous study, we studied the generalized nonlocal in time dynamics, okay, with a finite nonlocality, okay, a delta. Delta ranges from 0 to infinity, and this kind of dynamics can naturally bridge short time subdiffusion phenomena with the long time normal diffusion phenomena. And this kind of interesting phenomena has been observed in many experiments. Okay. Then also the nonlocal in-space model is also very popular to describe anomalous diffusion. For example, the trajectory of a particle's movement often involves some long distance jump. Okay, so here I just download a picture from Wikipedia. It is a migration trajectory of tiger sharks. So you can see, besides some short distance random walk, it also involves some long distance travel. Okay, and this kind of a process is called the Levé process. Okay, which is a generalization of Brownian motion. It involves the classical drift part, the diffusion part, and more importantly, it involves a jump part. Okay, if you ignore the first two part and just look at the third one, then the infinitesimal generator of this jump process is given by this integral form. Okay, if the mu is a symmetric and satisfies this specific form, okay, then you can write this operator as the integral with a kernel function k of x. A special case is the k of s satisfies this power law, then we will get the fractional Laplacian defined in this way, right? This is a very popular model when we describe the superdiffusion phenomenon. Okay, so in this example, we show the nonlocal in time and nonlocal in space model can help us to describe the anomalous diffusion, right? And the next example is the modeling in the fracture mechanics, okay? And this model is called paradynamics. It was proposed in 2000 by Stuart Schilling, and the key idea is to use nonlocal or integral operator to replace the special derivative in Newton's law. For example, the classical elastic model, okay, it is PDE model, it requires certain smoothness of displacement field. So when fracture is involved, you need some additional equation. Right? But for paradynamics model, it involves the nonlocal operator, okay, to replace the derivative in space. And it can model the continuous media and the cracks within a single framework. Okay, so it allows discontinuous solution. So people would like to use it to predict material failure. Okay. So up to now, I gave you some examples, okay, using nonlocal models, including model reduction or numerical analysis, anomalous diffusion, and fracture mechanics. And there are also other applications, okay, I list here. So hopefully I can convince you, right, the nonlocal models are both common and quite useful, right? So let me introduce something related to nonlocal models, okay, about the mathematics. So let's focus on the nonlocal boundary value problem, okay, on the bounded domain omega. And we consider this nonlocal diffusion equation, okay, nonlocal Poisson problem. Minus L delta U equals to F for X in omega. Here, L delta is a nonlocal diffusion operator. It's defined in this way. Okay, it is the integral over a small ball. Okay, centered at X, and the radius is delta. Okay, and the K delta is a kernel function, and Uy minus Ux. Due to the non-locality, when we define the boundary condition, we cannot use the classical boundary condition in trace type, okay, defining a hypersurface, right? So now we need to define this condition in a boundary layer, okay, out of omega. So it's something like that. Our equation is posed in this. Okay, this is a boundary operator, okay? Okay, it could be either Dirichlet type or Neumann type, okay? So the equation is posed in this domain, and the boundary is posed in a boundary condition is posed in this boundary layer. Okay, so it's a volume constraint boundary condition, and B delta could be the Dirichlet type. Okay, one X in the Dirichlet boundary region, or the Neumann type, one X in the Neumann boundary region, and the N delta is a Neumann operator, which will be introduced later. Okay, it can be derived using integration by part. okay, like the Green's first identity. And the kernel function k delta is non-negative, okay, and supported in the bore B delta 0, okay. The center is 0, radius is delta, and the second moment is finite. With this assumption, we can write the nonlocal operator in this way as an integral over the entire omega union omega delta. That is because our kernel function has this finite support. Okay, so these two expressions are equivalent to each other. And we can see this model is closely related to the local model as well as the fractional model. For example, if delta is small, we can choose this K1 scaling. Okay, K delta of S is 1 over delta D plus 2 times K1 S over delta. And this K1 satisfies this finite second moment condition. Then as delta goes to 0, the nonlocal operator will converge to the local Laplacian, right? Then we got the local model with the standard boundary condition. But for large delta, we can choose a different scaling. We can choose this K2 scaling. Well, K delta of S is a truncated fractional kernel. Then when delta goes to infinity, the nonlocal operator with finite horizon goes to the fractional Laplacian, right? And the boundary condition is imposed in the entire exterior domain, okay? And the proof is simple. So if you choose a smooth function and check, plug in the nonlocal operator, use the definition, then use Taylor's expansion, then you will see the leading term is a Laplacian, okay? And when delta goes to 0, the other terms goes away, okay? I don't want to say too much details. Then next, we want to check the well-posedness of the nonlocal models, okay? And the well-posedness could be verified by using the variational formulation, which could be found by integrating the strong form with a test function. So now we test L delta U with a test function V integrated over omega. And by the definition of the nonlocal operator, okay, we got the iterated integral. The outer integral is over omega. The inner integral, by definition, is over omega union omega delta, right? And that's the kernel times uy minus ux times v. Then we split this integral to two parts, okay? The first part is a symmetric part. So then we write it as the double integral over omega union omega delta square over omega delta square. Okay, excluding omega delta square. And the other part is still iterated integral. That's the integral over the boundary omega delta. Okay, that's a boundary layer. Okay, and the inner integral is on omega. Okay. Then if you look at the first part, we can write it as a symmetric form, right? We can balance u and v. We can write it as 1/2 a double integral over omega union omega delta square, excluding omega delta square, and the kernel function times uy minus ux, vy minus vx, okay? Balance the vu and v. In the second part, we move the v of x out of the inner integral, and it is just the integral over omega delta, okay? And the integrand is this blue part times v, right? So we can define this blue part as the Neumann operator, okay? So we define this Neumann operator in this way, right? That's the blue part. And the symmetric part is our bilinear form, okay? So after we test this v, okay, then we got two parts. The bilinear form and a Neumann operator times v, then integral over the boundary. Okay, so that's the nonlocal Green's first identity, right? Now to show the well-posedness, we need to define the energy space, which is a space involving consisting of our L2 function, and the bilinear form, okay, is finite. So this guy serves as a semi-norm in the energy space, okay? If you consider the Dirichlet boundary condition, you need the constraint energy space. Well, the function v belongs to the energy space and it equals to 0. 1x belongs to the Dirichlet boundary region. And the weak problem is to find a function u in this energy space such that it satisfies the Dirichlet boundary condition, okay, in the Dirichlet boundary region, and satisfy this weak formula. This weak problem, okay, the bilinear form is f inner product with v and plus an integral over Neumann boundary region. This is Neumann data and test function v. Okay. Now for simplicity, we only consider the homogeneous Dirichlet boundary condition and see the well-posedness. So first of all, we can check the energy space is indeed a Hilbert space. Okay, it has an inner product. It is complete. Okay, and we have a continuous embedding result. So this energy space is between the L2 space and the H1 space. Okay, it could be either closer to L2 or closer to H1. For example, that depends on the choice of kernel function. For example, if you choose a kernel function as a smooth kernel or integrable kernel, then it is equivalent to the L2 space. But if you choose the singular kernel function, like the fractional kernel function, then it is equivalent to some fractional sublevel space, right? And might be closer to H1. And we have the nonlocal Poincare inequality. So you can bound the L2 norm of U using the semi-norm of the energy space. Okay? And I want to emphasize this constant C could be independent of delta. So when you change the delta, this constant C will never change. Okay? And this shows that the semi-norm is actually a norm on the constraint energy space. Then by the standard argument using Lex-Milgram theorem, we can get well-posedness of the weak problem. And here are some asymptotic limits about the energy semi-norm. For example, for any H1 function, U, if you choose the K1 scaling of the kernel function, then when delta goes to 0, the energy norm converges to the H1 norm. Okay? Even though for fixed delta, this energy norm this energy space is weaker than H1 norm. Okay? And if you choose the K2 scaling and choose the fractional kernel, then when delta goes to infinity, for any H alpha function, the energy norm converges to the H alpha norm. Okay? In our previous introduction, I mentioned that for a smooth function, you apply the nonlocal operator on it, and if you choose the K1 scaling, then the nonlocal operator converges to the Laplacian. And actually, we can prove that if you choose correct scaling, then when delta goes to 0, the solution to the nonlocal operator indeed converges to the solution of the local problem. Okay? And this convergence relies on a compactness result proved by Bergain, Brazil, and Maronescu in 2001. So if the kernel function satisfies the K1 scaling and we let delta n go to 0, then for any sequence Vn belongs to the energy space with the uniform bound, okay, in energy norm, then this Vn is relatively compact in L2, and for any limit V is an H1 function, okay? Even though this is not an H1 function, but the limit is H1 function, and the bound of H1 norm is bounded by this constant C. Okay? Then combine this compactness argument, compactness result with the energy argument based on the variational formulation, then we can prove that when delta goes to 0, the solution to the nonlocal model converge to the solution to the local model. Okay, U0 means solution to the local PDE. Okay, and this guy converges to 0 strongly in L2 sense. Okay, and similarly, when delta goes to infinity, if we choose the K2 scaling, then in H alpha norm, the solution of the local model converge to the solution to the fractional PDEs. Okay, when delta goes to infinity. So you can see this nonlocal model naturally connects the local PDE as well as the global fractional PDEs. Okay. And finally, I want to mention a little bit. You can have some reformulation about the nonlocal model and the problem using the nonlocal differential operator in nonlocal calculus. Okay, for example, you can define the nonlocal gradient operator and the nonlocal divergence operator. Then the nonlocal diffusion model, nonlocal diffusion operator could be written as a composition of a nonlocal divergence and a nonlocal gradient. Okay, and your energy norm can be written as this form, which is more compact. Okay, and this nonlocal calculus is a systematic framework that mimics the classical calculus for the local PDEs. For example, the local PDE, we have differential operators, and in the nonlocal model, we have nonlocal operators, and both of them, we have a Green's identity and the integration by part formula. And for nonlocal model, we also have something similar. We have local balance compared with nonlocal balance, the local energy compared with nonlocal energy, and the boundary condition, okay, of a trace type. And for nonlocal model, we have a boundary condition of the volume constraint, okay, defined on the boundary layer. Okay, you can refer to the monograph of Professor Zhou, okay, for more details about the fractional calculus. So next, I want to introduce some popular numerical methods for solving the nonlocal models and explain what we need to care about. So for example, we can use the finite difference method to discretize the nonlocal operator. Okay, that's a method based on directly approximating the nonlocal operator by difference quotient. Okay, so we can construct a discrete nonlocal operator, okay, and solve the function value at each point. Or we can consider finite element methods. So we look for a finite dimensional subspace, okay, called W delta H. Then look for a solution, okay, or look for a function in this finite dimensional subspace such that it satisfies this weak problem, okay, for all test function in this finite dimensional space. For example, let's look at the Galerkin approximation. Well, we use Lex-Milgram theorem, we can prove the well-posedness, okay, same as a continuous problem. In the Galerkin orthogonality, the standard argument shows that our numerical solution is indeed a best approximation to the exact solution, okay, in the energy norm within this finite dimensional space. Okay, that's a standard argument. So if you fix the delta, okay, fix the model, and then let H go to 0, then you have the convergence. Okay, your numerical solution converge to the exact solution. Okay, if your finite dimensional space has a good approximation property. Okay, however, 1 and H go to 0 together. It was reported that if we use the piecewise constant finite element, then it will not converge if the delta and the H keep a ratio. But if you choose piecewise linear finite element, then the numerical solution always converges, and this convergence is independent of the relation of delta and H. Okay, then what is the reason? So we already know when delta goes to 0, the nonlocal solution converges to the solution to local PDEs. Okay, and for both nonlocal model and the local model, when H goes to 0, the numerical solution converges to the exact solution if you fix the model, right? And now we want to ask the question, what if H and the delta go to 0 together? Then we want our numerical solution to the nonlocal model, discrete nonlocal model, converge to the exact solution to the local model. And we want the convergence is independent of H and the delta. Okay, then we have this complete diagram. And this property is called asymptotic compatibility, okay, or AC, okay? So we want an AC scheme. Why we prefer AC scheme? Because the AC schemes are robust with respect to the problem parameter, okay? It is useful for validation and verification, and more importantly, it is suitable for variable horizon models. For example, if you consider the nonlocal local coupling, okay, model, or the nonlocal coupling model with different nonlocal horizon, okay, the AC scheme is very useful. Besides, the AC scheme is also very important when we design mesh-free methods for local PDEs, okay, as I introduced before in the SPH method. Okay. Then the next question is, what schemes are AC? Okay. Here is a simple example in one dimension. Now we consider this nonlocal diffusion operator, okay? It's the integral from minus delta to delta, u of x plus s minus u of x times a kernel function. Due to the symmetry, we can rewrite this integral as the integral from 0 to delta, okay? And write the integrand as u of x plus s plus u of x minus s minus 2ux, right? Times kernel function, same thing. Then we do a partition. We split the interval from 0 to delta into some small subintervals, and the length of subinterval is called h, okay? And this r is the ratio between delta and h, okay? Then we can approximate this integral by using direct Riemann sum, okay? So if you fix the delta and let h go to 0, you must have convergence, right? But now let's keep the ratio r equals to delta over h, and let's see what happened. Now we take a function u of x is x squared over 2. So the second derivative of this guy is 1, right? And also, if you apply this nonlocal operator L delta on this function, you will also get 1. But if you apply this discrete nonlocal operator on u, what you got just by a simple computation, you will see that your solution is a constant, only depending on this ratio r, but which is not 1, okay? So if you keep the ratio, there is always a gap between 1 and this constant, okay? So there is always a gap between continuous operator and discrete operator. So this implies if you fix the delta, then this approximation is good, okay? It's quite simple and it converges. But if you shrink the delta for small delta, this small delta will deteriorate the convergence. You will get a large error. And if the delta goes to 0, and if you fix the ratio between delta and h, okay, there is inconsistency between your numerical solution and the local solution. Okay, you never get the convergence. And you don't have this complete diagram, okay, lose a part of it. So actually we can revise this scheme a little bit to get an AC scheme. For example, we can divide by an S, okay, and times an S. And for this part, we take a piecewise linear interpolation, okay, operator. And this is just a linear combination of a nodal basis function, phi j, okay, and the coefficient is the function's value. Then after we do this interpolation, we approximate the nonlocal operator, okay, using some quadrature-based finite difference, okay. So we got a discrete form, and this is just a linear combination of a function value, and the coefficient aj is given by this explicit formula, which is just the integral of the basis function and the kernel function, right, times additional s. And this can be computed exactly. And for this scheme, we can prove that this scheme is quadratically exact. So that means if you plug in the quadratic function, okay, like x squared over 2, we choose as before, then the discrete nonlocal operator applying on it, we will get 1, which is just L delta U. Okay, so the discrete nonlocal operator applying on quadratic function is exact. Then you can check the difference between L delta H and L delta to see the local truncation error. So if your function is smooth, then the local truncation error is a second order in H. And it is important to see the constant C is independent of delta and H. Okay, that's important. Then besides that, we have discrete maximum principle. Okay, so this numerical scheme satisfies the maximum principle, and this further implies the scheme is stable. So that means the inverse of this operator in some norm, okay, in L infinity norm, is bounded by a constant C, which is independent of delta and H, right? Then combine this consistency with the stability, we can have the uniform convergence. So if you fix the delta, okay, then the scheme is the second order in H. Okay, and this constant C is independent of delta and H. Right? That's important. Now besides that, if delta and H go to 0 together, then the distance between your numerical solution and the local solution in infinity norm is bounded by H squared plus delta squared. And the leading constant is independent of delta and H. So when delta and H go to 0 together, your numerical solution converges to the local solution. And this convergence is independent of the relation between H and the delta, because in the error estimate, you split these two parameters. Okay, they are independent to each other. And this argument could be extended to multi-dimensional case on uniform grid. Okay, but you can see in the proof of AC property, we need to check the truncation error, and we need to check the maximum principle, okay, discrete maximum principle. But if you want to develop high order schemes, okay, it is very hard to develop high order schemes with discrete maximum principle, right? Maybe it's impossible, I don't know. So it's more reasonable to consider the Galerkin approximation if you want a high order approximation, okay, satisfy the AC property. So same as before, in this finite dimensional subspace, we look for a function u delta h. It solves this weak problem for all test function v in the finite dimensional space. And by the Galerkin orthogonality, okay, CS lemma, we know if delta is fixed, then your numerical solution converges to the exact solution, right? If you fix the model. But we want to check the AC property. Then how to do that? So actually, so here is a unified framework to check the AC property for Galerkin approximation. First of all, we need a uniform embedding property. So this energy space should be between the H1 and L2. And this has been proved, okay? And besides that, we need a asymptotically compact embedding property. So, and this has been proved by Bourgain, Brazil, and Mironescu in 2001. Besides that, we need the bilinear form be uniformly bounded and coercive. Sorry, here's a typo. This should be a little bit, right? And this is guaranteed by nonlocal Poincare inequality. And we need to also check the consistency of smooth functions. So that means if U is a smooth function, then you apply the nonlocal operator on it, and this guy will converge to Laplace U if delta goes to 0, okay, in strongly in L2 sense. And this is guaranteed by the Taylor's expansion and the definition of L delta if you choose a correct scaling. Besides that, the most important part is to check the approximation property of the finite dimensional subspace. So first of all, if you fix the delta, then when H goes to 0, your finite dimensional space will approximate the energy space, okay? That is a usual assumption. And the second assumption is called asymptotically dense in H01. That means for any H01 function V, you can find a sequence in the energy norm. Okay, Vk belongs to W delta K Hk. Okay, Hk goes to 0, delta K goes to 0, such that the Vk converge to V strongly in H1. Okay, and this assumption is quite strong. So with those assumptions, we can prove the AC property. Okay, for example, if your finite dimensional subspace contains or continuous piecewise linear element, so it contains all continuous piecewise function, linear function, then you can see we have this convergence, right? That's the properties of a piecewise linear function, the convergence in H1. So we can prove that this kind of scheme is AC, and therefore it is good for both non-local and local regions. But if we don't have the D2 assumption, for example, if the finite dimensional subspace only contain the constant, piecewise constant element, which is not a function, so obviously we don't have that. Okay. Then in this case, we can only prove the conditional convergence. Okay, the scheme is convergent only if the H over delta, this ratio, converge to 0. If you keep the ratio, the scheme never converges. Okay. And here I just sketch the proof. It's not hard. So when delta n goes to 0 and Hn goes to 0, then we have a uniform boundedness of our discrete solution, okay, in the energy norm, just by the energy estimate. And using the compactness result, this Un has L2 limit called U star, and this U star is a H01 function. Now we want to prove that this U star is actually the solution of a local PDE. Just check the weak problem, okay? Plugging this U star. And we can split this guy into 4 parts, okay? And a fourth part, okay, goes to 0 as n goes to infinity. The troublemaker is the third term. If we have the condition D2, we can prove that as n goes to infinity, this guy goes to 0. If we don't have D2, we need some extra conditions to guarantee this term converges to 0. Then we can only get this conditional convergence. Okay, and that condition often requires the ratio between delta and H. Okay, so that's the basic idea. And similarly, when delta goes to infinity, we can also prove this convergence, right? So if K delta satisfies the K2 scaling, then any conforming Galerkin approximation of the non-local model should be AC, okay? That means as delta goes to infinity, as H goes to 0, then your numerical solution converges to the U infinity. That is the solution to the fractional diffusion equation, right? And this convergence is strongly in H alpha. And this convergence is independent of delta and H. Okay. So this is a summary of numerical methods. So in this part, we have introduced so-called finite difference method and finite element methods for solving non-local equations. And the key idea is to check the AC property of the numerical scheme. Okay, and all AC schemes are insensitive to the change of model parameters. And when we check the AC property of a finite difference method, we require to check the truncation error and check the discrete maximum principle. And for finite element method, we can check the AC property using a general theory based on variational framework. And there are also discussions on some other methods of AC type, like the spectral methods or meshless finite difference, or meshless collocation methods. And then there are a lot of discussions on the numerical treatment for a special type of nonlocal models, called fractional diffusion models. Okay, if you're interested in those topics, you can refer to our paper published in 2020. So I want to stop here, and this is a take-home message. The nonlocal connections are ubiquitous in nature, and we introduce the nonlocal models with a finite range of nonlocal interactions, which serve as bridges connecting classical PDEs and fractional PDEs and nonlocal discrete models. And nonlocal calculus provided a systematic framework for analyzing nonlocal models and their local or global limits. And they are also important when we do the numerical analysis. When we numerically solve the nonlocal models, and we prefer to use asymptotically compatible schemes. And this kind of scheme are robust under parameter changing and desirable in a problem with multiple scales. Okay, and I will stop here, and thank you for your attention. Okay, thank you.
Any questions?
So I'm wondering, is there any study about the nonlocal model and numerical method for like maybe higher order linear PDE operator? For example, if you consider a biharmonic equation, which is a fourth order PDE. So is there any study about the nonlocal model and the numerical method?
As far as I know, I think Professor Zhou Qiangshi, where's he? Yeah. I think he has some studies on different models, including biharmonic. Yeah, I know he has some. But any numerical analysis results, or just the modeling? Right? Just modeling. Yeah. So for numerical analysis, I don't think there's some rigorous proof.
Okay, thank you.
Questions? No questions. So let's thank our speaker again.
Thank you.